Imagine a quiet winter evening in a major metropolis. Millions of people simultaneously turn on heaters, stoves, and water boilers. At that moment, the city consumes energy at a rate that no pipeline in the world could supply in real time. To prevent the system from collapsing due to a drop in pressure, humanity created invisible batteries, colossal underground reservoirs hidden a kilometer beneath our feet. These are not just empty caves, they are high-tech geoengineered facilities where natural gas is stored under staggering pressures of up to 200 bars. On a global scale, these storage sites hold trillions of cubic meters of fuel, providing 20–30% of all winter consumption for countries in harsh climates. But the price of such stability is a constant battle with the laws of physics. We pump a volatile, explosive substance into porous rock, effectively turning the Earth's crust into an overinflated balloon. The ultimate question for engineers is, how do you keep this balloon from bursting when millions of people live directly above it? Modern civilization suffers from a fundamental timing problem where gas production is a steady process, but consumption is a chaotic pulse driven by Arctic cyclones. Underground gas storage, UGS, solved this dilemma by acting as dampers. Without this system, any failure in a pipeline thousands of kilometers long would mean the immediate freezing of entire regions. While some regions struggle with gas, China faces a different geographic crisis. 80% of its water is in the south, but 64% of its farmland and half of its population are in the north. For decades, northern cities like Beijing have survived by drilling deep into the earth, but those wells are now producing sand instead of water. Beneath the streets of Beijing, the ancient aquifers are being pumped dry, causing the ground itself to sink by several centimeters every year. To the south, the Yangtze River overflows with billions of cubic meters of excess water that simply flows into the ocean. The solution sounds like science fiction. Move the river. China is currently executing the most expensive and complex hydraulic project in history, the South-to-North Water Transfer Project. It is a $62 billion attempt to rewrite the geography of a nation. This is not just a canal, it is a machine stretching over 1,400 kilometers. The project was officially approved in 2002, and since then, it has become a battlefield for engineers. The goal is to move nearly 45 billion cubic meters of water annually through 3 massive routes. The central route is the most daring because it relies entirely on the force of gravity. If the slope is off by even a few millimeters per kilometer, the water stops flowing, and the entire investment becomes a series of stagnant ponds. The starting point of the central route is the Danjiangkou Reservoir. To provide enough pressure to push water 1,400 kilometers north, engineers had to raise the height of the existing dam. They added nearly 15 meters of reinforced concrete to a structure that was already 30 years old. This created a massive challenge. How do you fuse new concrete to old concrete so that it can withstand the pressure of 30 billion cubic meters of water? Engineers used high-pressure water jets to strip the old surface and installed thousands of steel anchors to lock the 2 generations of masonry together. This increased the dam height to 176 meters, creating the gravitational head needed to start the journey. However, this expansion forced the relocation of 330,000 people, a social cost that highlights the sheer desperation for water in the north. The water now sits ready to begin a journey longer than the distance between London and Rome, driven by nothing but the weight of its own mass. Once the water leaves the reservoir, it encounters its first major obstacle, the Caohe River Valley. Instead of pumping the water down into the valley and back up, which would consume massive amounts of electricity, Chinese engineers built a bridge for the water. The Caohe Aqueduct is a 3-story tall concrete structure that carries the canal over the river below. Each segment of this aqueduct weighs 9,000 tons. To ensure the bridge wouldn't crack under the weight of the flowing water, they used a specialized movable scaffolding system that cast the concrete in place with 0 joints. The internal surface is polished to a mirror finish to reduce friction. But the real genius is in the joints between the bridge pillars. They are designed to withstand a magnitude 7 earthquake while maintaining a perfectly watertight seal, because a single leak at this height would erode the foundations and collapse the entire route. This structure allows the Yangtze water to soar over local rivers without mixing, maintaining its purity and its momentum as it travels toward the capital. The most terrifying part of the journey is the crossing of the Yellow River, known as the Mother River of China. The Yellow River carries so much sediment that its bed is actually higher than the surrounding land in many places. You cannot build a canal across it. Instead, engineers had to go beneath it. They deployed 2 massive tunnel boring machines with a diameter of 9 meters. These machines had to grind through a volatile mix of sand, silt, and high-pressure water. If the tunnel walls collapsed, the Yellow River would flood the entire South-to-North system. To prevent this, they used a slurry shield method, where a pressurized mix of clay and water is pumped to the front of the drill to balance the external weight of the river. Each meter of the tunnel is lined with high-strength reinforced concrete segments, sealed with double-layer EPDM rubber gaskets, designed to last for 100 years without maintenance. This is the peak of complexity, where technology must withstand the weight of one river while carrying another inside it. Between the Yellow River and Beijing lies over 500 kilometers of flat land. To keep the water moving without pumps, the canal must maintain a consistent downward slope. The engineering precision required here is staggering. The canal floor drops by only 2 centimeters for every 1,000 meters of distance. To achieve this, construction crews used GPS-guided excavators and laser leveling tools that are typically reserved for semiconductor manufacturing. Every section was scraped and compacted to a density that rivals a skyscraper foundation. The challenge is the soil itself. Parts of northern China have expansive soil that swells when wet and shrinks when dry. If the soil swells, it will crack the concrete lining of the canal. To solve this, engineers installed a multi-layer drainage system beneath the concrete, using geogrids and sand filters to keep the pressure beneath the canal perfectly stable, regardless of the weather. This ensures that the water maintains a steady flow speed of approximately 1 meter per second, reaching Beijing exactly when predicted. Maintaining a 1,400-kilometer concrete channel creates a unique biological problem. Over time, freshwater mussels and algae attach themselves to the canal walls. This creates microscopic turbulence, which increases hydraulic friction and slows down the water flow, reducing capacity by as much as 15%. To solve this, Chinese material scientists developed a specialized antimicrobial concrete lining. They infused the top layer of the cement with copper ions and photocatalytic titanium dioxide. When exposed to sunlight, these materials create a surface that is hostile to organic life without poisoning the water. Furthermore, every 200 kilometers they installed automated scraping stations. These high-speed brushes move along the canal walls, guided by sensors that detect biological buildup. This constant cleaning ensures that the water maintains its gravitational velocity, moving exactly at the speed calculated by the engineers years ago. While the central route uses gravity, the eastern route must move water uphill. This requires some of the most powerful pumping stations on the planet. They built 23 pumping stations that lift the water a total of 65 meters. The pump impellers are 6 meters in diameter, cast from a single block of stainless steel to prevent cavitation and corrosion. These pumps are so large that they are monitored by an artificial intelligence system that adjusts the blade angle in real time based on the flow rate. The main risk here is water quality. The eastern route uses ancient riverbeds that have been polluted by decades of industrial waste. To fix this, China built 400 wastewater treatment plants along the route. Every drop of water is tested for over 100 parameters, including heavy metals and pesticides, before it is allowed to enter the northern reservoirs. It is a massive purification machine that transforms industrial runoff into drinking water. When the water reaches Beijing, the task is not yet finished. For decades, the massive over-extraction of groundwater caused the geological layers beneath the capital to compress, causing the ground to sink. In some districts, the city was dropping by more than 10 centimeters per year. To combat this, engineers developed a secondary system of injection wells. Instead of just delivering water to taps, they are forcing billions of liters of Yangtze water back into the deep soil. They use a process called managed aquifer recharge. The water must be ultra-purified to prevent introducing bacteria into the deep earth. If the water contains trace organic matter, it can trigger biofilms that plug the soil pores. This engineering effort has successfully stabilized the city's elevation for the first time in half a century. It is a rare example of humans successfully reversing a geological trend, but it requires a constant balance of pressure to ensure the Earth does not shift unexpectedly. In a system that covers such vast distances, a single breach could be catastrophic. If a canal wall collapses due to an earthquake, billions of liters of water would flood the surrounding farmland, and the resulting drop in pressure would paralyze the water supply. To prevent this, the canal is equipped with over 60 automated sluice gates. These gates are controlled by a centralized neural network that monitors the water level at 10,000 different points along the route. If the system detects a sudden drop in pressure, the gates slam shut in less than 90 seconds. The gates themselves are made of high-strength alloy steel and can withstand the kinetic force of a moving wall of water. To manage the energy of suddenly stopping thousands of tons of moving water, engineers built surge basins at every gate. These tanks absorb the hydraulic shock, preventing the pipes from bursting under the water hammer effect. This level of automation is what separates this project from the simple canals of the past. Today, the South-to-North Water Transfer Project provides 70% of Beijing's tap water. It has replenished the underground aquifers and allowed the city to stop sinking. But the project is never truly finished. It requires a permanent army of engineers and a fleet of underwater robots. These robots use high-resolution sonar to scan the canal walls for cracks while the water is still flowing. The $62 billion project has succeeded in preventing a national disaster, but it has tied the fate of the North to a single thread of concrete. If one segment fails, the capital city faces an immediate drought. It is a testament to human engineering and a reminder of the massive cost of fighting the natural order of the planet. If you want to see more deep dives into the engineering that reshapes our world, make sure to subscribe to the channel. Leave a comment below. What do you think is more impressive? Moving a river through the mountains or storing a nation's energy beneath the ground? We'll see you in the next one as we explore the LNG mega tankers or the physics of deep-sea pipelines.